Hi, everybody. This is Rob Rader. I'm Director of Engagement and Membership here at AGU. Thank you so much for joining this Atmospheric Sciences webinar series. This is the final webinar in an 8-part series called From the Past into the Future, which is based on the presentations given at 2019 Fall Meeting by Atmospheric Sciences section. This was a centennial session at the Fall Meeting. For today's speakers, we have Ben Santer, who is going to present fingerprinting the climate system. And then we have Brian Soden, who is going to present progress and challenges in understanding the atmospheric hydrological cycle. Before we do that, just want to mention that we will be recording this, so you can feel free to watch it afterwards or share it with your colleagues. We also will have a Q&A after each presentation, so if you have questions, you'll be able to ask them through the software, as well as raise your hand. If you've got a mic and you'd like to talk to the speakers, you'll be able to do that as well. So without any further discussion from me, we're going to go ahead and pass this over to Ben to get started. Let's see. All right, Ben, whenever you're ready. Thanks so much for joining us. Appreciate it.
Good morning, ladies and gentlemen. Hope you're all safe and well. I wanted to talk to you today about the history of fingerprinting the climate system. Let's see. I'm not able to advance the slides here, Rob.
If you just click the screen, the slide doesn't advance, Ben?
Oh, now it does.
Okay, great.
So before getting into the history of fingerprinting, I wanted to tell you about two things that profoundly influenced my scientific career. The first was in my early 20s, falling about 150 feet in a crevasse, climbing the north face of the Aiguille d'Argentière. And I remember looking up at this thin slit of blue sky 150 feet above me and recognizing that if I reached that thin slit of blue sky, I'd be able to be back in the realm of the living. No matter what happened with IPCC, Congress, no matter how bad things got subsequently, life has been gravy after getting out of that crevasse. The other seminal event in my life was in Madrid in November 1995, nearly 25 years ago now. We were in this beautiful Palacio de Congresos in Madrid for 3 days at the plenary meeting of the second assessment report of the Intergovernmental Panel on Climate Change. And at that meeting in Madrid, we finalized these 12 words, the bottom line findings of the Detection and Attribution chapter of the second assessment report. The balance of evidence suggests a discernible human influence on global climate. And those 12 words changed my life too. And I'm going to reflect a little bit at the end of my presentation about some of the lessons learned from crawling out of the crevasse or climbing out of the crevasse and from the balance of evidence finding. But now on to the history of climate fingerprinting. So I'm going to first try and give you a brief overview of some of the principal developments. And this is an idiosyncratic personal view of the world of detection and attribution. And I'm going to do it decadally. So in the 1970s, I think the major developments were in the climate models themselves, from simple radiative convective models to more complex models of the atmosphere and eventually of the ocean, physical insights, for example, as we ramp up CO2, the troposphere warms, stratosphere cools, improving observations, transitioning from land surface temperatures to land plus ocean, beginning to make, with satellites, measurements of atmospheric temperature and many other state variables. All of this is happening in the 70s. Then we transitioned to the 80s, And folks in the detection and attribution arena start studying global scale changes, say in surface temperature, and try and look at the basic signal to noise properties of different variables, different regions, and then begin to think about the benefit of going from global means to looking at complex patterns of change, so-called fingerprints. In the 1990s, we have the first and second IPCC reports, the first report in 1990, the second in 1995, more complete description and understanding of anthropogenic effects on climate. So moving beyond use of changes in greenhouse gases alone to understanding that anthropogenic aerosols are also important, and we have to understand and represent them in simulations of historical climate change, and the actual application of pattern-based fingerprint techniques to surface and atmospheric temperature. One of the criticisms of the second assessment report was that if there is a human-caused climate change signal lurking in observations, it should be manifest in more than just temperature. And the third and fourth IPCC reports took heed of that criticism and concern and moved well beyond temperature-only studies, looking at many different aspects of the climate system, hydrological cycle, cryosphere, upper ocean. They also moved beyond looking at global scale patterns of change to regional detection and attribution, and even to event attribution. So looking at how human-caused climate change might influence the likelihood of specific threshold crossing events. And multivariate studies looking at multiple variables at the same time. In the most recent decade, we have the fifth IPCC report, more detection and attribution with extreme events, quasi-operational event attribution, where people pretty much in real time try and look at a specific extreme event and very rapidly analyze and estimate the human contribution to the likelihood of that event. The use of large initial condition ensembles in detection and attribution, and doing detection and attribution not just with broad brush temperature, moisture, but with more impact relevant variables as well. So I'm going to go through these decades one by one and highlight some of the seminal events and papers. So let's start in the 1960s. And in 1967, we have one of the most famous papers in our field by Manabe and Weatherald. Here's a picture of very early Suki Manabe in 1960s at GFDL in Princeton. And Suki and others were developing simple radiative convective models and exploring the role of greenhouse gases, water vapor, and carbon dioxide in maintaining and changing the thermal structure of the atmosphere. This is from that very famous 1967 paper. And what you can see there on the left is a figure, a slice through the atmosphere, global mean, from the surface right up into the stratosphere in pressure. And Suki and Dick increased atmospheric CO2 in this simple radiative convective model from 150 to 300 to 600 parts per million, and saw that as they did that, the stratosphere cooled and the troposphere warmed. And this was at a time when we didn't have the satellite data and arguably the weather balloon data to determine whether the stratosphere was actually cooling and the troposphere was warming. So it was truly a prediction. As we ramp up CO2, this is what we should see. And we'll look later at whether this prediction was correct or not. In the 1970s, there were some other seminal events. One was a study by Bob Shervin and Steve Schneider back in 1976 that recognized that a GCM simulation with human-caused changes in greenhouse gases was not going to yield pure signal. it was going to yield signal plus the noise of natural internal variability. And the key insight was that scientists had to use statistical techniques to separate the climate response to the thing you changed from the noise of natural internal variability. And how do we do that? In 1979, there was the very famous Charney Report. I'll get onto that in a minute. A seminal paper by Klaus Hasselmann that sort of laid out fingerprinting and why it was necessary to move beyond analysis at individual grid points. And it also marked the first year of satellite-based estimates of atmospheric temperature, true global scale measurements of the temperature of the troposphere and the stratosphere. So I'm going to take you through two of these, the Charney Report and Hasselmann's paper. And the Charney Report, again, this is over 40 years ago now, pretty much said that if we double atmospheric CO2, we're going to get warming, best estimate about 3 degrees with an error plus minus 1.5 degrees C. And we know that if we're going to continue to pump CO2 into the atmosphere, we are going to change the climate system. This was 41 years ago, and it was a pretty clear warning to the scientific community and to the rest of the world. Then Klaus Hasselmann's paper, in a rather obscure conference proceedings, Meteorology over the Tropical Ocean, clearly mapped out the importance of looking at patterns, that we needed to try and separate signal from noise by looking at complex spatial patterns, and that was a much more efficient way of partitioning signal and noise than looking at individual grid points. It was a key insight, as I'll try and convince you later. Then in the 1980s, we see many developments in terms of looking at signal to noise properties. Where are the canaries in the coal mine? Is it better to look in the tropics and the extratropics for a human-caused warming signal? In 1982, there's the first DOE workshop on detection of carbon dioxide effects, a very influential workshop at which there was considerable discussion of fingerprinting. Tom Bell in 1983, building on Hasselmann's 1979 ideas, thought quite a bit about this business of trying to optimize a fingerprint. In other words, to look in a direction where the signal of human effects on climate was likely to be large relative to the noise of natural climate variability. Then in the late 80s, you see Tim Barnett and Mike Schlesinger trying to do fingerprint detection in earnest in the real world and apply these Hasselmann and Bell insights to real world tropospheric temperature data, surface temperature data, and learn by doing. Then in 1988, there's Jim Hansen's very famous JGR paper, where he famously claimed in a full AOGCM simulation that we were close to detection of an anthropogenic warming signal in observations. Tom Wigley and Bob Charleston and others, Joyce Penner, in the late 1980s began to look at sulfate aerosol effects on climate and recognized that greenhouse gases aren't the only game in town, and we also needed to understand the complex, spatially and temporally heterogeneous effects of aerosols on climate. This is just one example from Barnett and Schlesinger in 1987. You see on the left, they had actually looked at a number of different variables and tried to assess their signal to noise characteristics by looking again at pattern information, and concluded that surface temperature and upper air temperature had better signal to noise properties. So the signal was spatially distinct from the patterns of natural variability. Sea level pressure, they concluded, was a poor place to look for a model predicted CO2 signal. So this was very valuable work setting the stage for where do we look what are the best places to look for human effects on climate. In the 1990s, we have the first IPCC report and their bottom line statement: the unequivocal detection of the enhanced greenhouse effect from observations is not likely for a decade or more. And I'm just going to take you through a few of the findings of that report. Remember, this is 30 years ago now. So one finding was that global mean temperature was a suboptimal variable for doing detection and attribution work. So there was this clear statement in the first IPCC assessment that we really needed to look at patterns. There was also a clear statement about what detection and attribution are. The signal is the space-time dependent response to human-caused changes in greenhouse gases. For example, the noise is natural internal variability. And if we want to do attribution, we want to find signals that can be uniquely attributed to a specific cause. Another interesting thing that I'll get back to later was the clear statement in 1990 in the Detection and Attribution chapter that tropospheric water vapor was probably a good place to look for a human-caused fingerprint. Based on model analyses, it had a high signal-to-noise ratio. Problems were that the records weren't very long, but this might be a good place to look. And that's what the community actually did, as I'll try and convince you later. Another clear statement, this is the final one I'll show you, was that back then in 1990, they could not clearly and unambiguously identify a human effect on climate, but this didn't mean that the greenhouse effect didn't exist. So there was a clear statement. We're dealing with the detection of a signal that is gradually emerging from the noise. We can't do detection and attribution now in 1990, but this doesn't mean that our models and theory and basic physical understanding is wrong. So very clear statements worth going back 30 years and looking at some of the conclusions of the report. In the 1990s, we have then a lot of efforts to try and understand internal variability using an energy balance model, Wigley and Raper, using statistical models, even quite advanced statistical models fit to observations, using a full AOGCM, Ron Stauffer and Suki Manabe, beginning efforts to simulate the combined response in GCMs to greenhouse gas and aerosol forcing. We have the IPCC second assessment report and its discernible human influence on climate conclusion. We have Jerry North and collaborators looking at space frequency fingerprinting and recognizing that forcings like solar forcing have specific frequency characteristics that we could and should exploit in order to identify and separate solar effects on climate from human effects on climate. And then more fingerprint studies in the real world involving the vertical profile of atmospheric temperature change and Gabi Hagel's famous work in 1996 looking at surface temperature and applying Hasselmann's optimal detection techniques. Then Hasselmann in 1997 saying, hey, wait a minute, we've got both greenhouse gas patterns and aerosol patterns. Let's try and detect them simultaneously in observations. And Gabi's 1997 work that did just that with surface temperature. In 1999, Miles Allen and Simon Tett began to recognize that it's really important to do formal statistical tests of how well models capture our best estimates of observed climate variability and build confidence in the reliability of model-based internal variability estimates. So this was sort of the bottom line statement from Gabi's 1996 paper. that a human effect on climate has been detected, but there are still caveats about the magnitude and patterns of internal variability. This was a seminal work. In the 2000s, we have people like Miles Allen and collaborators recognizing that detecting and essentially sort of quantifying a model predicted fingerprint in historical observations could be used to constrain uncertainties in model climate change projections. And that was the beginning of efforts to use DNA techniques to constrain projection uncertainties. Then in 2001, we have the IPCC third assessment report, going far beyond the cautious balance of evidence finding of the second assessment report and concluding that most of the warming observed over the last 50 years is attributable to human activities. So making a quantification statement of the size of the human effect. We also begin in the early 2000s in Nathan Gillett's work to transition from doing detection and attribution with individual models to using large multi-model ensembles like CMIP3, for example. Then moving beyond temperature again to things like tropopause height, sea level pressure. Peter Stott's famous paper in 2004 trying to do event attribution with the 2003 European summer heat wave and calculate the so-called fractional attributable risk. So how did human-caused warming change the probability of something like the 2003 European summer heat wave? Tim Barnett and colleagues continued to explore innovative avenues in detection and attribution, looking at the vertical structure of upper ocean temperature changes. Folks at the Hadley Center began to look at temperature extremes. In 2007, we have the fourth assessment report going and upping the likelihood language from the third assessment report. See the inclusion of that very likely due to observed increase in anthropogenic greenhouse gases. Then we start transitioning to detection and attribution with elements of the hydrological cycle that Brian will discuss later. Precipitation, Western US hydrology, so runoff, snowpack, and water vapor. So this is from Peter's famous Nature paper with the European summer heat wave, where a clear statement was made that human activities were not only changing the broad brush climate, but contributing to the change in likelihood of a specific extreme event. I would argue that was a bit of a breakthrough. I'm going to tell you a little bit about our water vapor work that I just mentioned. In 2007, we published a paper claiming that we had identified an emerging human-caused warming signal in the moisture content of Earth's atmosphere, looking at SSMI measurements of total column water vapor, and that this signal was primarily due to human-caused changes in greenhouse gases. We were criticized, quite rightly, and our critics argued that we had done this in a model democracy. We had used 22 different models, and we had judged them to be all equally credible in terms of how well they captured water vapor, observed water vapor behavior. So in responding to that criticism, we completely redid the analysis and chose top 10 and bottom 10 models using 70 different metrics. The bottom line was that the signal, the response of water vapor to human-caused forcing, was pretty similar, regardless of how we tried to fold model quality into the analysis. Water vapor increased everywhere, and the largest increases in water vapor were over the warmest areas of the tropical oceans. In contrast, model-based estimates of natural climate variability in water vapor showed this canonical El Nino type pattern with areas of water vapor increase and decrease. So there was really this orthogonality between the human influence pattern on water vapor and the natural variability patterns, regardless of how we selected models. And that, in the end, was why we were able to confidently identify a human effect on atmospheric water vapor. Getting to the end now, most recent decade, of course, the so-called pause in warming, slowdown in warming, was a big issue for our field. Susan Solomon and colleagues did a lot of work trying to understand the effect of moderate post-2000 volcanic eruptions, the effects of water vapor changes, the effects of ozone changes during that period. We have Dave Pierce looking at salinity for one of the first times and upper ocean temperature. Clara using large ensembles to do detection and attribution work. The IPCC fifth assessment report, fingerprinting with clouds, discussion in Nathan's paper in 2016 of DMIP or DNA MIP, which really is a targeted exercise involving single forcing experiments, some exploration of forcing uncertainty. So simulations designed to be really helpful for detection and attribution. The National Academy report on attribution of extreme events, the release of the fourth National Climate Assessment, which I would argue was an act of courage in current times, and use of large ensembles in pattern-based fingerprinting with impact-relevant variables like the Palmer Drought Severity Index. So the bottom line in the fifth assessment report was we see human influence everywhere in the climate system, not just in temperature, but in many different aspects of the climate system. So 18 years after the cautious balance of evidence finding, this was a fundamental shift. The conclusions are that we really have, in the last 50 years, identified human fingerprints in a number of different aspects of the climate system. The old second assessment report criticism, you're only looking at temperature, is no longer valid. We see human influence in many different independently monitored components of the climate system. And it's that physical and internal consistency that is so powerful and compelling. Also, this is not the work of one group, this is the work of an entire scientific community. 4 personal lessons learned from the 2 experiences I mentioned at the beginning. Defend scientific understanding. There's no point in being a scientist if you're unwilling to defend the hard-earned scientific understanding you've gained. Never engage in science by eminence of position. Do the research necessary to address the criticism you receive. Don't just preach to the choir. Speak to people who are skeptical about what you do and what you've learned, and declare your values. And just finally, while I'm waiting for questions here, I'll declare my values. So in addition to being a climate scientist, I'm also a climber. These are pictures that I've taken all around the world during my lifetime as a climber in the Alps, in the Himalayas, in the North Cascades, most recently on the Juneau ice field. And these places have value for me. Over one human lifetime, I've seen profound changes in these beautiful, fragile, high alpine environments. And in addition to the scientific imperative to understand the causes of these changes in snow and ice, we also need to have a discussion about values. What do they mean? What do they mean to us if we lose them, if they're no longer there for all of us to enjoy in the way we've been able to? So this isn't purely a science question, but also a question of human values. So I'm happy to answer any questions that you might have. Thank you very much for your attention, and please stay safe and well.
Thank you so much, Ben, for that great presentation. Appreciate it. I do have a couple of questions for you here, so I'm going to go ahead and ask those. From Agnes, welcome Agnes. Is it possible to compare pre-industrial revolution versus present time to infer anthropogenic effects?
Sorry, I didn't understand that question, Rob.
I'll say it again. Is it possible to compare pre-industrial revolution versus present time to infer anthropogenic effects?
Yes, it is, Agnes. So virtually all detection and attribution work makes use of so-called control runs. And these control runs are sort of world without us simulations. They are initiated often from pre-industrial states of the atmosphere. So pre-industrial concentrations of greenhouse gases and aerosols, and climate modelers run these simulations for centuries, and that gives us an estimate of the background natural variability of the climate system on monthly, decadal, and century timescales. Then the same model is used with our best estimates of historical changes in greenhouse gases, aerosols, land use, and other external forcings. And by comparing the world with us and the world without us, we can make some good inferences about how human-caused forcings changed the climate system. And that is done now not in the context of one individual model, which is the way things worked back in the 1980s and 1990s, but you can do this comparison of pre-industrial climate with today's climate with pretty much all the climate models in the world. And that's powerful because you can look at uncertainties in our model-based estimates of the signals in response to anthropogenic forcing and the noise of natural climate variability, and you can determine whether something you really care about, like ability to identify a human fingerprint in observations, is sensitive to those model-based uncertainties in the signals and in the noise of natural variability.
Thank you, Ben. Could you talk a little bit, this is from Deep D, could you talk
Any
a little
other
bit
questions,
about,
Rob?
yep, from Deep D, could you talk a little bit about what you think the future is, the field of detection and attribution?
I'm sorry, Rob, I'm not hearing you. Would
I'm
it be
not sure
possible
what's,
to write the question in the chat box?
sure, I can try that.
I'm sorry, I did not hear any of that question. Oh, thanks for writing the question. So the question was, could you talk a little bit about what you think is the future of the field of detection and attribution? Well, I think one of the key things we have to do is better constrain uncertainties in anthropogenic aerosol forcing. And that's a challenge for the detection and attribution community. It has been for at least the last 25 to 30 years. There's a lot of uncertainty in aerosol effects on climate, particularly indirect aerosol effects on cloud optical properties, cloud lifetimes. So how can we in the detection and attribution community, using spatial information, using seasonal information, using vertical information, better constrain those currently still large uncertainties in anthropogenic aerosols? And I think there's some promise there. Our physical understanding tells us that different forcings have different, not only spatial patterns at the surface, but also different seasonality and different vertical structures. How do we exploit all of that a priori physical understanding with the latest, greatest satellite observations to better constrain uncertainties in direct and indirect aerosol forcing? To me, that's one of the major challenges that I'd like to work on in the next couple of years. Thank you very much, everyone. Please stay safe and well.
Thank you so much, Ben. I appreciate it. So we're going to go ahead and move now to Brian Soden. Brian, can you hear me okay?
Yes, I can hear you fine, Rob.
All right, great. So I'm going to go ahead and make you the presenter. So you should be able to share your screen now. My apologies to a couple of the questions that did come in that we weren't able to get to. We'll be sure to share those with Ben offline and try to get answers to those for you. So thanks to everybody for participating. Thank you to Ben for the great presentation. And now I will hand over to Brian for his presentation on progress and challenges in understanding the atmospheric hydrological cycle.
Okay. Hi, everyone. I hope you're all well. It's nice to have a chance to talk to someone that is not related to me for a change. So I appreciate the organizers for putting this together and letting me do this. So yeah, I'm going to talk about the atmospheric hydrological cycle. And when I was, putting this together, I did a little research to look at, what the history of our understanding of the hydrological cycle was, and came across this nice review paper by Chris Duffy that discusses how our thinking about the hydrological cycle has evolved over time, going all the way back to the ancient Greeks. And of course, a lot of early civilizations were formed along rivers, so there's a natural curiosity to try to understand where all this water was coming from. What was the source of the rivers and springs that was so critical to their cities? And well, the atmospheric hydrological cycle was much more interesting way back then, and much more interesting and exciting models of it. And there's some illustrations of it here, but there was this idea that rainfall alone could not explain all the runoff that they were seeing in the rivers and so forth. So they had one of the concepts was something known as this reverse hydrological cycle. It's sort of illustrated in some of these diagrams where they had whirlpools out in the ocean that would suck up water and carry it through subterranean channels up into the mountaintops, where it would kind of, I guess, bubble out in these caves and come out the sides of the mountains as springs. So, unfortunately, the real hydrological cycle isn't quite this exciting. But one of the points that is made in this review paper is how there was still this recognition of the need for a balance, that the rivers didn't exist in isolation, but there was a balance of fluxes and between the reverse hydrological cycle and the river runoff. And so there was an actual cycle there. And of course, that's central to how we think about the hydrological cycle today in terms of a balance of fluxes. But it wasn't until the early 1800s that we actually had enough, measurements and information apparently to really satisfy ourselves that we could explain all of the runoff that we see on land just through precipitation alone. So we didn't need these subterranean caverns to carry water up in the mountains, but there was actually, it was the atmosphere that was lifting vapor and condensing it aloft, and then that was the source of river runoff. But we still rely on this central concept of a balance of fluxes to really use that perspective in understanding the hydrological cycle and changes in the hydrological cycle. So with that as a little preamble, here's the outline for my talk, and I'd really like to talk about and touch on 5 main concepts, which first are what are the global constraints that we have on the hydrological cycle, in particular on water vapor and precipitation. How does that help us shape our understanding of what future changes in the hydrological cycle will look like? And then how are changes in the hydrological cycle linked to changes in the atmospheric circulation? What are the pattern of changes in precipitation minus evaporation? And how does an increase in moisture lead to increase in extremes in P minus E, or extremes in rainfall? And then lastly, and I'm not sure if I really have time to touch on this, but I'll make a few comments about understanding regional projections of precipitation change. So to get things started, we'll look at water vapor and precipitation, and first water vapor. Then, of course, water vapor is important for linking evaporation and precipitation itself, but it also plays a critical role in climate. It is separate from its role in the hydrological cycle. So it is, of course, the dominant greenhouse gas, and that's something we've known since work by Tyndall back in the late 19th century. Here's a nice quote from him where he notes that water vapor is a blanket more necessary to the vegetable life of England than clothing is to man. And shortly after that, there was work by Arrhenius and also T.C. Chamberlain in understanding changes in climate and the ice age, and they really recognized the importance of water vapor as a feedback mechanism. And Arrhenius is more implicit, but here's a very clear quote by T.C. Chamberlain in trying to understand the cause of the ice ages, where he invokes water vapor and the temperature dependence of water vapor to provide a positive feedback on the climate system to help explain how you could get these large changes in climate between the ice ages and the current climate. And interesting, he also referred to carbon feedbacks as well and invoked those in understanding the ice ages. So he was, in addition to his sort of hipster beard here, he was a man ahead of his time in the scientific front as well. And it is this temperature dependence of water vapor is really essential, both for the hydrological cycle and for climate change as a whole. And to really illustrate the importance of water vapor feedback on climate sensitivity, this graph shows how the climate sensitivity and the intermodal range in climate sensitivity is shown here in blue, and how that depends on the strength of water vapor feedback. So the sort of canonical range of climate sensitivity that Ben referred to earlier, all the way back to the Charney Report, is sort of 1.5 to 4.5 degrees centigrade, and that's shown here by this red arrow. But if we eliminate water vapor feedback, if we could magically make water vapor feedback 0, we would be all the way over here on the left hand of this curve. So not only is the amplitude of warming greatly reduced, but also the uncertainty in future climate sensitivity is also reduced, because water vapor not only amplifies the sensitivity, but it amplifies the uncertainty in other feedback mechanisms. So without water vapor feedback, really global warming wouldn't be a problem. We would have a maximum warming of about 1.5 degrees and a minimum warming of 1 degree. So it would be both relatively certain and relatively small compared to what its actual estimated range is. And of course, on the other side of that is that if we made water vapor feedback just a little bit stronger, maybe 10% stronger, the upper bound on climate sensitivity would go from 4.5 degrees up to 6 degrees. So it's very important to really have confidence in the strength of this water vapor feedback, because small changes in its magnitude can have a big impact on climate sensitivity. And it really wasn't until while there was an appreciation for the temperature dependence of water vapor, it really wasn't until the advent of satellite observations that we could fully appreciate just how dominant this temperature dependence, how dominant of a control it has over water vapor in the real atmosphere. And this is an early paper by Graham Stevens using simmer measurements that plotted the precipitable water, which is the column integrated mass of water vapor, as a function of surface temperature. And you can see that there's this very clear increase in water vapor over warmer oceans. And the that relationship is perhaps even more impressively seen if you look at the time evolution of total precipitable water here. These are more recent measurements, satellite measurements from the SSMI instrument these are near global average over oceans only, shown in red, and these are anomalies. You can see these large fluctuations and this long-term increase in water vapor that we've seen over the last 30 years, 35 years. And then the black line in gray shading shows simulations from the CMIP6 models from AMIP simulations where they're actually forced with the observed evolution of ocean surface temperatures. And you can see they do a remarkably good job at reproducing not only the trend, but also the fluctuations on these subseasonal timescales. So this really illustrates the really strong connection between temperature and water vapor and just how dominant temperature is in controlling changes in the amount of water vapor. And this is, of course, central to other constraints on the hydrological cycle, not just our confidence in water vapor feedback. And of course, as Ben mentioned earlier, sometime by around the mid-2000s, we already had a large enough trend that we could discern this and attribute this increase in water vapor to human activities rather than just natural fluctuations alone. However, the feedback from water vapor, total column water vapor is really a measure of water vapor in the lowest part of the atmosphere, in the boundary layer primarily. And most of the feedback from water vapor is actually in the upper levels of the atmosphere. So total column water vapor itself doesn't really give us a good insight into how the upper troposphere is changing. But there are other satellite measurements that show that. And here's a graph showing the changes in upper tropospheric water vapor taken from a combination of HERS and MSU measurements. And we can see again that there's been this clear long-term increase in upper tropospheric water vapor over the last 40 years, and that is consistent with model projections. So not only is the total column of the atmosphere moistening, but the upper levels are moistening too, and this is really essential and really important to have confidence in our projections of climate sensitivity as a whole. Now, if we take that picture of water vapor changes and compare it to how precipitation is changing over this same period, you see a very different picture. And here's that same plot I showed for total column water vapor, only now using the precipitation anomalies from SSMI and comparing them to CMIP6 models. And you'll notice, by the way, obviously there's no really clear trend. And a number of studies, a recent one by Bob Adler, has shown, again, quite clearly that even if you use perhaps better quality and better QC measurements than SSMI, it's difficult to discern a significant long-term trend in global mean precipitation. And you can see that here. And despite the fact that there's this clear increase in clear temperature dependence in the amount of water vapor. So that tells us that changes in mean precipitation, either the time average or spatial average precipitation, really aren't controlled by the amount of water vapor in the atmosphere, which may seem a little counterintuitive. But there's other processes that are controlling the changes in precipitation. And to really understand what changes or what controls these changes in precipitation, we have to consider the energy cycle. And this coupling between the water and energy cycles has become very prominent and really defines how we think about these two exchanges. And to the point we have an entire WCRP project that is named after this close coupling between energy and water cycles. But there are really two scientists, I think, that brought this perspective to prominence. Sugi Minabe, as Ben referred to earlier, with his really benchmark work in understanding the role of and a coupling between the water and energy cycles from the atmospheric perspective, and then Budico from the surface perspective, understanding how the coupling between evaporation and surface energy fluxes, and using that to understand how evaporation would change. So those two scientists really, I think, established the groundwork for looking at the coupling between energy and water cycles. And that's something that's continued on today. Using this approach to understand how precipitation will change in the future. That perspective was sort of repopularized by a paper by Allen and Ingram in 2002 called Constraints on Future Changes in Climate and the Hydrological Cycle. And here's a figure from a paper by Stevens and Ellis that sort of illustrate quite clearly this coupling between, on the x-axis here is shown changes in the net atmospheric radiative cooling in a warmer climate. And on the vertical axis is the change in latent heat release due to changes in precipitation in a warmer climate. And each of these boxes here are global averages from a model. So as the climate warms, when we add CO2, the radiative cooling increases. And that rate of cooling increases in large part because the atmosphere is just warmer, so it's emitting more thermal radiation. And that increase in radiative cooling needs to be offset by something. And it's offset by an increase in precipitation, an increase in latent heat release. So we can really think of the role of precipitation is essentially to offset the net rate of cooling of the atmosphere. And so as the atmosphere warms, it cools more, and as it cools more through radiation, there's an increase in latent heat release to balance that change. Now, we still really rely on this coupling between energy and water cycle to understand changes in the hydrological cycle in the warm climate. A number of studies have more recently added new insights into this perspective. This top graph is a figure from Pendergrass and Hartman that shows that, again, changes in radiative heating on the horizontal axis and changes in latent heating on the vertical axis. But what they show here is that most of the change in precipitation can be explained just by changes in the clear sky radiative cooling. So it's nice for a chance not to have to worry about clouds. Clouds are so important and so uncertain in many other aspects of the climate system. But for understanding changes in the hydrological cycle, we can really just focus on what's controlling changes in the clear sky radiative cooling. So that was a big help. And it turns out, a paper by DeAngelis kind of followed up with this and showed that most of the spread in the clear sky radiative cooling is actually due to spread in shortwave absorption by water vapor. And you might ask, why is there so much uncertainty about the shortwave absorption by water vapor? And the answer is that, well, there really isn't. This is actually, we understand how much absorption there is by water vapor quite well. This is just really an artifact of having poor parameterizations of rate of absorption by water vapor in our model. So we can tighten this up quite a bit just by improving the parameterizations of radiative transfer using existing knowledge. It's not really a true uncertainty here. Other recent work, and I'll talk about this in a minute, is how the radiative forcing from CO2 itself acts to provide a net heating of the atmosphere, and that tends to also reduce the need for precipitation. So there is a CO2 effect that tends to reduce precipitation, but a warming effect, an atmospheric warming effect that increases radiative cooling and demands more precipitation. And so it's the balance of those two that really come into play. And then lastly, using things like radiative kernels, we have a better understanding of how different portions of the atmosphere contribute to this increase in radiative cooling. And we know that the increase in radiative cooling, or we can better appreciate that this increase in radiative cooling in a warmer climate is really dominated by the lowest levels of the atmosphere, really within the boundary layer. And it's also fairly flat, spatially flat, and that there's not a lot of meridional structure here. And it turns out that also is important because that tends to drive the spatial structure in the response of evaporation. And so we tend to get a relatively meridionally flat response of evaporation because in part of this flat structure responsive rate of cooling in the atmosphere. So next, moving on to the second topic is how is the circulation coupled to changes in the hydrological cycle. And we can think of this, again, going back to this comparing the changes in precipitation to the changes in water vapor. Precipitation tends to increase much more slowly. So precipitation only increases by about 1 to 2%, or maybe as much as 3% per degree Kelvin, whereas the amount of water vapor in the atmosphere increases much faster, at about 7% per degree. So if the circulation was not to change, we would expect precipitation to increase at roughly the same rate as the water vapor mass is, because as convective updrafts are carrying moisture up, the upper troposphere really can't hold that much water vapor because it's so much colder, so most of that water would precipitate out. The fact that precipitation increases much more slowly, therefore, means that the upward convective mass flux must be weakening in a warmer climate, and that's exactly what we see, a decrease in convective mass flux in a warmer climate. And in fact, overall, just a weakening of the overturning circulation in a warmer climate. And again, that can be a little counterintuitive. You might think that a warmer climate would be more energetic, but actually the overturning of the atmosphere and the kinetic energy within the atmosphere actually weakens in a warmer climate. And that's due, again, to this disparity between the rate at which water vapor increases versus the rate at which precipitation increases. And again, the rate of precipitation increase is being dictated by the rate of cooling. So we typically think of about a 5% per degree weakening of the atmospheric circulation. And an early study by Becky et al. In 2006 looked at, I should back up a second. One of the interesting things about that weakening is in model projections, that weakening of the overturning circulation occurs almost exclusively as a weakening of the zonally asymmetric circulation, like the Walker circulation, rather than a weakening of the Hadley circulation. It's really dominated by the zonally asymmetric component. And so what Becky et al. Did was look at patterns of sea level pressure change, and what they found using an observational record that went through the 1990s was a weakening of the Walker circulation. And that was very consistent with what models were projecting, and you could actually do an attribution of this weakening and show that the observed weakening was largely due to anthropogenic activities rather than natural fluctuations. However, since the time when this paper came out, the Walker cell has actually strengthened over time. So there's a bit of a mystery going on here about what is happening with the atmospheric circulation itself. There are some studies that suggest that just there's very large internal variability, and that is dominating the changes in the overturning circulation, especially the Walker circulation. So that changes in the Walker circulation with our observational record are still really being dominated by internal variability rather than an anthropogenic weakening. And that may be the case, but the arguments regarding the precipitation, circulation, and water vapor mass changes still sort of necessitate a weakening to be happening somewhere. So if the Walker circulation isn't weakening, are there other aspects of the zonally asymmetric circulation that are weakening in place of it, or is everything just being masked by large internal variability? I still think there's a lot of work that could be done here to sort of further understand that. And next, moving on to patterns of changes in precipitation minus evaporation. So I showed earlier that in terms of a global mean, the precipitation changes are largely are very difficult to detect in terms of a global mean precipitation. But if you look at the spatial structure, you see very clear changes in that. And we can understand this in terms of just this increase in water vapor. So what I've shown here on this top graph is a pattern of precipitation minus evaporation, where the red and orange regions are regions where precipitation is greater than evaporation, and the purple and blue regions are where E is greater than P. And so these regions represent, respectively, areas where water vapor is being imported. There's a net import or a net export of water vapor. And so as we increase the amount of water vapor, if we neglect changes in the circulation and just increase the mass of water vapor, we would expect an increase in moisture import for the import regions and an increase in moisture export for the export regions. So just by this change in moisture convergence or divergence, we would expect the patterns of P minus E change to look much like the patterns of the P minus E in the base climate. And that's in fact what we see. And that leads to this idea of wet regions becoming wetter and dry regions becoming drier. And that can explain most of the first order changes we see in terms of the pattern of P minus E change. And in fact, it can also guide us on how to better detect changes associated with changes in the hydrological cycle. Rather than looking at global means, we should exploit this contrast between wet get wetter and dry get drier to look for signatures of an intensified hydrological cycle in this sense. And we can in fact see that. If we look at salinity trends, we see salty regions getting saltier, that's the dry get drier, and fresh regions getting fresher. So that's the wet get wetter, and we can see that being manifest in ocean salinity trends, which are sort of a good integrator of P minus E. But also, if we look at just precipitation trends themselves and break the precipitation trends up into wet regions and dry regions, again, we get a much more detectable signal where wet regions are becoming wetter. I've had a hard time saying that, and dry regions are becoming drier. I'm going to skip this just to catch up and move on to sort of the second to last topic here, which is looking at how the variance of P minus E and how that relates to an increase in precipitation extremes. So we know that as we increase the amount of moisture, while that doesn't directly relate to control the change in mean precipitation, it does have a big constraint on changes in the variance of precipitation. And there's a nice paper, again, by Angie Pendergrass at NCAR that looked at CMET5 models and show that you get this consistent increase in the temporal variance of precipitation across a wide range of timescales, from daily, increase in the daily variance of precipitation, increase in the seasonal variance of precipitation, and an increase in the mean or the extreme precipitation. And these changes occur at a much faster rate than the mean precipitation increases. So, you know, that's an important consequence, and it's a direct result of this increase in water vapor that is due to the strong temperature dependence. And again, as Ben alluded to earlier, we can also look at these in observations, and there are clear observational trends that are consistent with the model projections, and several studies that have done attribution of an increase in the precipitation variance and precipitation extremes that can be attributed to human activities. So we're already seeing the human impact of on the changes in the extremes in the hydrological cycle. One area that's still, I think there's still uncertainty about is if we, and that's shown here, this is a paper from O'Gorman that looks at the zonal structure or the meridional structure of changes in extreme precipitation. And what they've shown is that in the extratropical regions, that extreme precipitation events increase at about the same rate as water vapor mass does, about the Clausius-Clapeyron rate of 7% per degree. And there's relatively little intermodal spread. But if you look in the tropical regions, and this black line with gray shading here represents sort of bias-corrected or constrained model projections, what it shows is that there's a much larger, extreme precipitation events increase almost twice as fast as the Clausius-Clapeyron rate, and there's a much larger intermodal spread. And it's not clear yet why there is this amplified response of tropical precipitation extremes to a warming climate. Why is there this super Clausius-Clapeyron rate of increase? A couple of possibilities are that it's due to an increase in convective aggregation in a warmer climate. or that it's possibly there's some temperature dependence in the microphysics that leads to an increase in precipitation extremes of the tropics. So this is another area I think that's sort of ripe for further study. And then lastly, I'm not going to go through any slides here, but just a couple comments about regional precipitation change. And that is two things. One, that uncertainty in regional precipitation change isn't due to the same thing that uncertainty in climate sensitivity is. So it's not due to uncertainties in cloud feedback or whether we have a low climate sensitivity or a high climate sensitivity. And it's also, studies have shown that the regional patterns of precipitation change, at least over land, are not really sensitive to the pattern of future warming. So if it's not sensitive to how much global mean warming there is, or it's not sensitive to the pattern of warming, what is really the cause of these uncertainties in regional precipitation? And it turns out that I think there's a lot of evidence that points to it's really a reflection of biases in the model's simulated mean state. So and that's reflected in biases in mean circulation. So and this dependence is even explicit in the wet get wetter idea. So wet getting wetter is saying that there's the change depends on the mean state, and that's certainly true at the regional level. And so one way that we can try to improve regional projections of precipitation change is to improve our ability to simulate the mean state in these models. And with that, I'll just summarize the main points of my talk. The mechanisms behind global mean changes in precipitation and water vapor are really pretty well understood. We understand the importance of the Clausius-Clapeyron dependence and the coupling between the energy and water cycles to help constrain those. There's still a bit of a mystery about the weakening of the circulation. Is the overturning circulation actually weakening? Can we observe it? Or is it being dominated by internal variability? The regional details of the wet get wetter, I skipped over this slide, but they're sensitive to a couple of things like the spatial patterns of surface warming and spatial shifts in circulation that can be induced by aerosol forcing. Increased variance is a very robust projection and one that we have confidence in because it really depends on the increase in the water vapor mass, which again, we have good reason to be confident in. And we can already detect those changes in observations. And regional projections, which are so important for adapting to climate change, really require improved simulation of the mean state in models. And with that, I am all done and happy to take any questions.
Brian, thank you. Appreciate that. So I do have one question right now. Other folks would like to ask a question. You can feel free to do so now. We've got a few minutes to cover some questions. And you can do that in the questions part of your control panel, or you can raise your hand virtually and we can have you ask your question. So the question that came in here from Agnes, what event do you think will help the trends for water vapor and precipitation from the model, since the changes in precipitation and water vapor content is in sync with the trends?
Okay, so sorry, can you just repeat that one more time for me? So
sure, and it came in around 10 minutes into your presentation, and I know it might not be specifically what it's about, but what event do you think will help the trends for water vapor and precipitation from the model, since the changes in precipitation and water vapor content is in sync with trends?
Well, if I understand the question correctly, in terms of events, there's two things I think that really give us confidence in the changes in water vapor, for example, and that the ENSO variability we see gives us a very large signal that we can compare to, and we see a strong temperature dependence there, and the models are quite capable of reproducing that, and also of course the long-term trend in water vapor increase. And for precipitation, we have to be a little bit smarter in how we look at it. We can't. It's difficult to look at it in terms of global averages because there's this. Unlike water vapor, there's regions of large increase and regions of large decrease. Whereas for water vapor trends, we usually see a pretty consistent increase. So for precipitation, if we separate it by wet regions and dry regions, then the signal becomes quite clear and quite robust. And so I think that's that's a sort of a smarter way of analyzing precipitation trends.
All right, thanks, Brian. From Marcus, I was impressed by the model observations match on changes in variance of precipitation, particularly because my understanding was that models still didn't match rainfall intensity very well. Have models improved, or is the trend robust despite intensity mismatches?
Yeah, that is a very good point, actually, that there is this tendency for models to drizzle too much, to have too much light rainfall and not enough heavy rainfall, so they don't distribute it good. So that's actually a very good comment on that. I don't believe that the models have really gotten much better in that, although I could be proven wrong on that. So in part, again, it arises from this strong dependence of the variance, the temporal variance on the change in temporal variance on the change in water vapor mass. So in fact, you can argue that the temporal variance should increase at roughly twice the rate of Clausius-Clapeyron. I won't go into details of that. And so that gives us a very robust projection because we are so confident in the increase in water vapor mass.
All right, thank you, Brian. Thank you for the question. From Linda, are the PPT predictions consistent with observed desertification? And then in parentheses, actual land changes.
Oh, so are the P-E projections consistent over land? Yeah, land gets a little bit trickier. The wet get wetter, dry get drier works very well over oceans where you have an unlimited capacity to evaporate, which is obviously not the case over land. But much of the desertification over land is associated with again, this coupling between the water and energy cycles. But over land, many of the regions, especially the drier regions, are water limited. So if the atmosphere is increasing the rate of cooling, it's demanding more heating to offset that cooling. And the land can't provide all of that in terms of local evaporation. It helps to compensate by increasing the sensible heat flux rather than the latent heat flux into the atmosphere. So this increase in sensible heat flux requires a warmer surface. So that's one of the reasons that land tends to warm up faster than ocean surface, in addition to differences in heat capacity and so forth. But the inability to offset the rate of cooling purely or primarily from an increase in evaporative heat flux demands an increase in sensible heat flux. An increase in sensible heat flux is achieved by warming the land faster. And that in turn, because most of the source of moisture comes from over the ocean, which hasn't warmed as much, that leads to a reduction in relative humidity over land, which further amplifies the land warming. So land gets more complicated, I guess is the bottom line of that. I don't know if that chain of logic that I outlined there makes sense, but it still involves these couplings between water and energy cycles, but it's a little bit more complicated.
Well, Linda says thanks. That was a helpful response. So that's great, Brian. Also, some comments coming in about the great presentations. So thank you for that. I don't see any other questions or hands raised at the moment. So I think with that, we are a little bit over here, almost at 1:15. So I'm going to go ahead and end the presentation. If anybody would like to reach out, feel free to do so. You can always reach out to me, Rob Rader, rradar@agu.org if you have any questions for the presenters. But I just want to thank Brian for your presentation. Thank you, Ben, for yours. Appreciate your time today. We do, again, record these, so we'll be sharing those recordings with everyone. They are on the Atmospheric Sciences website. Jim Hurel and Paul Newman are the president and president-elect of the Atmospheric Sciences section. So feel free to reach out to them with questions or ideas or ways you might want to get involved. They do a great job of running the Atmospheric Sciences sections, and always love hearing from members. So appreciate their work on getting this webinar out to our members. These are ways right now that you can stay connected with AGU. All of these webinars will be uploaded to our YouTube channel. This is the final webinar in the series of 8. So thank you to all of our speakers, all 15 speakers over these last few weeks. This has been a great series. And thank you to the members for joining us, spending time with us. Again, these are ways you can reach out. The main page of AGU has some COVID-19 information and responses and resources. So feel free to check that out as well. All of the AGU honors programs have been postponed till June 1. So if you haven't gotten that nomination in that you've been thinking about, you've got time. That's all I've got right now. Thank you so much, everybody. Appreciate everyone's time today. And everybody stay safe and stay well, and we'll see you all soon.
And thank you for running these, Rob.
Oh,
Yes,
it's my
thank you.
pleasure. Truly. Thank you, guys.
Thanks, Ben.
Take care.
Brian. Great talks. Be safe, stay healthy.